Hi, in this video we are going to see how BFGS algorithm it is implemented in DIgSILENT. We are going to see step by step. The name comes from Broyd and Fletcher Goldfarb and Shano algorithm. Which is an iterative optimization method for solving nonlinear optimization problems. This algorithm is a quasi-Newton method, which means that the Hessian matrix is not directly computed, but instead it is iteratively approximated using info from the gradients and from successive points. So at the the input of the algorithm is like this. We have a number of iteration, 500. We have the dimension of the problem, 5 in this case. Tolerance, a very small number in which the algorithm stops. Then we have the lower and upper bound of the variables, -5 and 5, and the test function. We have here 1. So we have inside in content, we have a script with 19 test functions, and we choose the first test function, which is the simplest, is the sphere function. Okay, so the first step is to determine the starting point. Actually, this is the first approximation of the solution, which is a random value, as you can see, a random value between lower bound and upper bound. Here is the matrix. Actually, it's a matrix of 1 row and 5 columns in this case. But we are going to say it's a vector. Okay, so we have the solution vector, initial solution vector, which is randomly constructed. Then we are going to compute the gradient of this vector. As you can see, we have here the script for computing the gradient, which has as an input the test function number 1 in our case. O is an object, which is actually the first approximation, and grad is a vector where the gradient it is written. We are going to enter inside the gradient. As we can see, along with the 3 inputs, we have another input. It is epsilon, which is a very small number, which is the perturbation, which is going to be added to the vector. So the gradient vector is like this. First, we have this. We take the size of the solution, which is 5 in our case. So we are going to iterate from 1 to 5. We are going to construct 2 copies of the solution vector. Yeah, 2 copies, in which in first copy of the solution vector we are going to iteratively to add a perturbation, the if element, and then to the second vector we are going to to subtract epsilon from the if term, and then just compute the value of the objective function for the first vector and then for the second vector. And the gradient formula, it's exactly the one from the literature, a minus b divided by 2 multiplied by epsilon. A being the first objective function, b being the second objective function, where the epsilon was subtracted. Okay, so in the end we are going to obtain gradient with 5 values. Okay, further we are going to enter the main loop. It is from 1 to 500. Okay, and then first thing to do is to compute the convergence when the algorithm to stop. It is not economically to go all 500 iterations. So when the convergence is checked, it's going to the algorithm is going to finished. Check convergence subscript has as an input the gradient vector, which is going to compute the norm of the vector. I'll go a bit in check convergence, and we're going to see that here the convergent is computed as a square root of the sum of the squares of each element from the gradient. Actually, is the norm of the vector, a typical norm. Okay, and if that value is smaller than the tolerance that we initially defined, then the algorithm stops there. Then, very important step, sorry, is to compute the direction of search. The direction of search from the literature is the minus of the inverse of the approximated Hessian. Yes, this is the inverse of the Hessian multiplied with the gradient, with the search direction, which is the search direction. Yeah. Then further, we have here another loop from 1 to 50 in this case, in which we must determine the value of alpha. What is alpha? Alpha actually, if we are going to go a step further, where the solution is updated, and we have here the new solution, it is equal with the previous solution, plus alpha, which is determined in the previous step, plus, multiply with the step. So in the previous step, the alpha is computed because it is, if it is very big, it's going to make huge leaps in the solution domain, or if it is too small, it's going to take forever, and maybe it's going to get stuck in the local minimum. So alpha is computed here in the previous step using Armijo condition, or I don't know if it is the proper name. Yeah, is one of the two conditions from the Wolf conditions. We are going to see them, the Wolf conditions. The Wolf conditions are these ones. First, f of x plus alpha multiply with the search direction to be smaller than f of x plus c, a very small number, alpha, and search direction and the gradient. So that formula is implemented here. Sorry, in Armijo here. Okay, and here we have the condition f is greater than f2. So this is the condition to remain the loop. If f1 is smaller than f2, then the flag is going to be remain 1. Yes. And if it's going to remain 1, it's going to go out, break out of the loop. And then the alpha determined here is going to be used here to compute the new solution. By computing the new solution, we are going to compute the gradient of the new solution, as I said it earlier. So we have first approximation with its gradient and new solution with its new gradient. Having these four values, let's say, we are going to compute the differences. The differences, meaning the step in the parameter space and change in the gradient. So step in the parameter space is vector S, where new solution, which is computed as new solution minus the old solution, the previous solution. And in the gradient, change in the gradient, it is new gradient and previous gradient. Having S and Y, we are going to compute the inverse of the Hessian matrix approximation, which is this formula, along with this. This formula is computed here, and here is the final result. Let's see how it should look. As you can see it here is a 5x5 matrix because we have a dimension of 5. Then further we are going to update the variables. Yeah, here O is equal with the new solution and grad is equal with grad new. Okay, so that's it. Simple as that. The loop is going to run until 500, or if the convergence is checked, until then. Further, we are going to run the algorithm for the sphere function, but we are going to use here a dimension of, let's say, 10. That's 5. Okay. So we are going to see how fast in a small dimension the algorithm works. So execute. So that's it. We have the solutions we have 5 solutions. As you can see, they are almost 0, exactly like in the literature. If you are going to see, wait a bit, here it is, for the sphere function, the solution was going to be 0. Okay, so now let's compare this quasi Newton method with Newton method, that Levenberg-Marquardt algorithm that computes the direct Hessian matrix. So once again, BFGS computes an approximation of the Hessian matrix, and the Levenberg-Marquardt is computed the direct. Computed direct Hessian matrix is more time consuming. So if we run the algorithms, we are going to see that Levenberg-Marquardt algorithm is going to is going to compute slow. So we're going to put here 50. So for 50 dimensions, execute. As you can see, was very simple, even smaller than a second. But now, if you run the same optimize the same objective function with Levenberg-Marquardt algorithm, it's going to be a bit time consuming. As you can see, first iteration, second iteration, third, so on and so forth. So this is the great advantage of the BFGS algorithm that is very useful in large dimensions. So as you can see, also it obtained very good results, but it took 20 seconds. Yeah. Further, I would like to discuss about the main drawback that this algorithm has over the genetic algorithms and particle sort optimization algorithms. So the algorithms such as Levenberg-Marquardt algorithm and BFGS that that directly computes the inverse of the Hessian matrix or an approximation of the inverse Hessian matrix has as a main drawback the fact that they are getting stuck in local minimums. So they are behaving very well in some test function, such as sphere function, such as Rosenberg function, or Himmelblau function. So they are behaving very well here in this kind of test function where the domain is smooth, yes, with few or just one minimum, local minimum, and they are behaving very poor in test function as Rastrigian, yes, Oakley function, which has a lot of ups and downs, local minimums, yes. And on the other side, the genetic algorithms and particle sum optimization, due to the way they are searching the definition domain, they are behaving very well not very well. They are behaving, let's say, good in all distance the test function. This is the main advantage of the genetic algorithm, in particular some optimization, that they are behaving good in all of them. Not excellent, as the derivative algorithm do in few of the test function, but they are behaving good in all the test functions. Now let's see the comparison between this type of algorithms and the genetic algorithm to see exactly, to point out exactly what I said. Okay, so we will run BFGS for the fourth objective function. The fourth objective function in this case is going to be the rastringy function. So we can see it is a type of objective function that where the algorithm will not behave with our algorithm will not behave very well because it has a lot of local minimas. Yes. Okay, so we should obtain 0 with 0 for the for two dimensions, and the value of the objective value to be 0 to reach the global minimum. Okay, so the 4 minus 5 with 5, so 2 dimensions. Let's run the algorithm. As you can see, we do not have here 0 with 0, and the value of the objective value to be 0. Once again, run the algorithm. As you can see, we will not get the global minimum. As you can see, once again, we didn't obtain it. Let's do the same thing with LMA, which computes directly the inverse of the Hessian matrix. Okay, 4, 2, okay, execute. Same thing, we didn't obtain 0 with 0. Once again, now let's go in binary genetic algorithm. As I told you, it will obtain the optimal value or around the optimal value. Test function 4 minus 5, 5, 2 dimensions. Let's execute the script. As you can see, we directly obtain 0 with 0. Yes. We run it once again. 0 with 0. As you can see, it's exactly what I told you, that binary genetic algorithm, it behaves very well for all these test function, but our algorithm, actually any kind of gradient that uses the gradient, algorithm that uses the gradient, behave well with simple test functions, such as fair functions, such as Rosenbrock or the Himmelblau. Okay, that's it. Thank you.